Firstly, intervention under the control of the investigator to either change something or introduce meaningful variation in conditions. Number 2, and implied directly by number 1, the existence of a comparison group, a condition or state which permits the evaluation of the effect of the treatment. Number 3, the allocation of cases to treatment and control conditions by some sort of randomization device. Randomization is the key element, with experimental subjects allocated to the different experimental conditions by some kind of lottery-like device. For a small study, this may be as crude as drawing well-mixed numbered slips of paper from a hat. In principle, there is no limit to the number of treatment conditions, and we are certainly not restricted to studying just the presence or absence of the treatment. In a negative income tax experiment, for instance, we may be interested not only in the contrast between subjects who did or did not receive payments, but also between subjects who received different levels of payment. What the control condition is will vary depending on the context of the study. In a lab experiment, it's usually not sensible for the controls to literally do nothing while the treatment group complete whatever tasks they have been assigned. So the control group must be given a task known not to have a systematic relationship to the outcome. In other situations, the natural control condition for a new treatment might be the best treatment currently in use. Sometimes the randomization is carried out in such a way that neither the investigator nor the subjects know what conditions each subject is in. The double-blind procedure is typical of medical trials, but is often impractical in other contexts. If we are evaluating a job training program, we can't hide from the participants who is receiving the training and who isn't. One of our chief worries, in fact, in this kind of study, is that those in the control group might feel themselves deprived of the benefits they believe the treatment will bring, and, as a consequence, avail themselves of a close substitute for the training that they are missing out on. The part randomization plays in causal inference is often misunderstood or misrepresented. Randomization in an experiment is not the same as random sampling in a social survey sense. In an experiment, randomization plays a role only in making an inference about the group of subjects included in that particular experiment. Generalization to other groups and populations is a separate issue. Randomization in an experiment acts as a probabilistic ceteris paribus condition. Consider a setup where we were able to run an experiment a very large number of times, each time allocating subjects to the treatment and control condition at random, with everything else being exactly the same. The only ex ante difference between replications would be which subjects were allocated to which condition. Imagine we knew that sex and age were related to the outcome variable. On average, over a very large number of replications, the proportion of men in the treatment and control groups would approach equality, as would the proportion of the young. In general, on average, over a large number of replications, we would expect the composition of the treatment and the control group to be virtually identical. When they are identical, they're said to be balanced. But so what? How is that relevant to making an inference from the single experiment that we've actually conducted? The argument is that the randomization, combined with a sharp null hypothesis of no difference in outcome between the treatment and the control group, allows either the exact calculation of the probability of observing a difference between the outcome for the two groups as large or larger than the one actually observed, of course all the time conditioning on the truth of the null hypothesis, or the estimation of this conditional probability. Thus, even though in any one experiment there is no reason to believe that we will have achieved exact balance between the treatment and the control groups with respect to the almost infinite number of factors that could potentially affect the outcome, we still have a warrant for a statement about the likelihood of observing a difference of the magnitude we observe if it were the case that in reality the outcomes in the treatment and the control group were equal. And that warrant comes from the initial randomization, which allows us to infer what, in probability, the distribution of the unobserved, possibly confounding factors will be. And that, at a minimum, is all we need to know, though of course we will be able to make better inferences if we're able to make fuller use of other prognostic information. To fix ideas, let's do a little revision about how we make an inference in an experiment about a treatment effect. Imagine we had the simplest setup shown on this slide. Two groups of subjects, randomized, indicated by the red R, to two conditions. The treatment is given to the first group, indicated by the black cross, and nothing or something irrelevant is done to the second or control group. After a suitable period of time, outcome measures are taken for both groups. This is represented by the blue Y1 for the first group and the blue Y2 for the second group. And our interest is in whether the average outcome for the treatment group differs from the average for the control group by some amount that is of substantive importance. To make things more interesting, we're going to mimic this setup in a computer simulation in which we will put ourselves in the godlike situation of A, knowing the true value of the average treatment effect, and B, being able to repeat the same experiment many times so that we have some idea of the range of ways that things could have turned out. In our simulation, we will divide 200 subjects equally into two groups, 100 in the treatment group and 100 in the control group. Of these 200 subjects, 100 are female and 100 are male. But initially, we're not going to make use of that information in the randomization. Because we are godlike, or at least because we're in control of the simulation, we know the process by which the outcome, in this case denoted Y, is generated. It's generated according to the formula Y equals 0.4 times treatment plus 0.4 times sex plus epsilon, where epsilon is drawn from a normal distribution with mean equal to 0 and standard deviation equal to 1. So individual level variation in the outcome is influenced by the treatment, whether you're female or male, and by a lot of idiosyncratic factors that may differ between people and between replications of the experiment. By construction, treatment is uncorrelated with sex, and epsilon is uncorrelated with treatment and sex. Our objective in the experiment is to estimate the average treatment effect, and we have the unsurpassed advantage that, of course, we already know what the answer is. A typical situation is that we attempt to draw an inference about the average treatment from a single experiment. A single experiment represents just one of the many possible randomizations of the subjects to the treatment and control groups. We're going to study many randomizations, all with the same basic setup. In other words, we're going to see what happens when we are in the happy situation of being able to repeat our experiment over and over again, with the knowledge that the process generating the individual level variation in the response is the same on each occasion. What is going to differ is which subjects are randomized to the treatment and control group. In principle, it would be possible to exhaustively examine all possible allocations of 200 subjects to two equal-sized groups. There are 200 factorial divided by 100 factorial times 100 factorial unique different ways in which 200 subjects can be allocated to two same-sized groups. This is a very large number, approximately 9 followed by 58 zeros. Thankfully, it's not necessary to enumerate them all, and it's sufficient for our purpose to run our experiment only as many times as it takes to get a good idea of the distribution of the possible outcomes. We will run our experiment 10,000 times, and on each occasion record the outcome. So here is a schematic of the algorithm I use. 1. Create 200 cases to represent the 200 subjects. 2. Assign them a sex, either female or male. They will retain that sex throughout all of the replications of the experiment. 3. Generate a random number and sort the cases on that number. 4. Assign cases to the treatment or control condition. The first 100 to the treatment, the second 100 to the control condition. 5. Generate the outcome for each case. 6. Calculate the average treatment effect and save it. 7. Repeat. 8. Calculate some summary statistics and draw a histogram depicting the distribution of treatment effects. For those that are interested, a stata-do file for implementing the simulation can be downloaded from the following URL. So how do things turn out? The histogram represents the distribution of the average treatment effect estimated in the 10,000 replications. You can immediately see that the distribution is centered on the true average treatment, in this case 0.4. But we can also see a lot of spread around the average of the averages. We could have got an estimate as low as minus 0.15, implying the treatment made things worse, or as high as 0.9, which would lead us to be very optimistic about the efficacy of the treatment. The 2.5th percentile of the distribution, represented by the green vertical line, has a value of 0.11, and the 5th percentile, represented by the orange vertical line, has a value of 0.16. True, most of the estimates are concentrated around the true average, but normally we only run the experiment once, and we can't rule out that we might have been unlucky and drawn one of the randomizations that gives us an estimate at the 2.5th or the 5th percentile, or in fact even further out in the left tail of the distribution, even though the true treatment effect is 0.4. On the face of it, this sounds worrying. How can we ever know what the true treatment effect is? The short answer is that, unless we're God, we can't. Asking for a method that will enable us, on the basis of a single sample, to infallibly find the Holy Grail is to ask for something that doesn't and can't exist. What we can do is make an estimate and try to evaluate how good that estimate is. All we need for that is a procedure with known properties that allows us to form a very good idea of the variability in the estimated average treatment effects. Randomization and our relatively large sample size supply that. In this particular case, we can simply calculate empirically that if we form an interval according to the rule estimated treatment effect plus or minus 1.96 times the standard deviation of the distribution, which in this case is 0.15, then approximately 95% of those intervals so constructed will include the true average treatment effect. So now we have a sense of a plausible range of values for the treatment effect, and a sense of how unlucky we would have to have been not to have calculated one that contains the true average treatment effect within it. You will undoubtedly have encountered this form of reasoning before. It's what you're doing when you construct a confidence interval. It is, of course, important to remember what a confidence interval tells you. After observing the data and calculating the interval, it does not tell you the probability that the true value is within the interval. That value is either 0 or 1. It either isn't or it is within the interval, but it will remain in and of itself unknown and unknowable. Likewise, statements to the effect that you are 95% confident that your interval contains the true value have no objective content and are not warranted by the procedure. The fact that they may quantify your private personal beliefs about the matter is quite irrelevant. It's also not true that having constructed a particular interval, 95% of the estimates obtained from repeated sampling would fall within it. If we construct an interval centered on 0.16, the fifth percentile in our empirical distribution, it should be obvious that 95% of the distribution can't possibly lie within it. The only correct statement is one about the nature of the process you've used to construct your interval. If you were to use this method repeatedly, then 95% of the intervals so constructed would contain the true average treatment effect. Unfortunately, it's also easily calculated from our simulation that 23% of the intervals also contain the value 0, implying the possibility that there is no treatment effect. We'll return to this worry in a moment, but first I want to say something about covariate balance.